Hey, this is Math 8, Unit 5, Lesson 18, scaling 2 dimensions. And so on our last lesson we were scaling only 1 dimension. Now we're looking at what happens when we change 2 different dimensions. So for example, if I'm talking about the area of something where I have a length and a width, right? So I have an x and a y. If I change both of those dimensions by making this one perhaps a little bit longer, then also making this one a little longer as well, that's going to change the overall area of that shape there. So by just doing both dimensions, it changes 2 things. So the area is going to change quite a bit here, wouldn't it? If I just did one, if I just did the x and not the y, then it's only going to change a little bit, right? So it's only changing this much here. But if I do both, I have a greater amount of change that's taking place there. And that's what's taking place in today's lesson. We're going to look at what happens when we change 2 dimensions of a 3-dimensional object and how that impacts the volume, whereas before we were just doing 1. So let's take a look. First of all, we have these statements here called tripling statements. We're going to say they're all positive integers, and we have 2 different equations where m equals a plus b plus c, and n equals a times b times c, right? Multiplying those out. So let's see which ones are true. Okay, if a is tripled, m is tripled. So let's see, that would look like this. M equals, if we triple a, you have a, 3 times a, plus b, plus c. Is that going to result in that being a tripled value by just multiplying that by 3? We'd probably say, no, that's not going to happen. It's going to just increase that 3 times. That will increase, but not 3 times as much, because you still have b's and c's are the same. We have a, b, and c are all tripled. Does that triple m? Well, think of this. We have 3a plus 3b plus 3c. Because we're tripling every part of that, then yes, the value of m is going to be 3 times as much what it could have been, because it's 3 times all the way through. So that'd be a true statement for 2. First, for this one, if a is tripled, what happens to n? Well, we have n equals 3 times a times b times c. Because we're doing multiplication, because that's tripled, that means the result will also be tripled as well. What happens with multiplication? It doesn't work with the addition one, but multiplication, yes. So if a, b, and c are all tripled, n is tripled. That would look like this. 3 times a times 3 times b times 3 times c. Well, that's a lot more than times 3. That's a 3 times 3, which is 9, times 3, which is 27. That would result in a 27 times n. So a lot different than just 3 times as much. And then you can create your own true statement based upon what you see up there as well. Let's move to today's lesson here. So it says, first of all, we have a square base. Claire sketches a rectangular prism with a height of 11 and a square base and labels the edges of the base as S. Right? So she has a rectangular prism which has a height of 11, but it has a base that's a square that happens to be S. So we have S and S. So there's our square base down here, and it has a height of 11. Okay, so that's our volume there. So our volume in a sense is volume equals S times 11. So volume equals S squared times 11, or 11S squared is what the volume is going to be for the shape that she draws. She asks how what he thinks will happen to the volume if the rectangular prism, if she triples S. So if S becomes 3 times as much, he says the volume will be 9 times bigger. And the question is he right? So let's see. Let's take a look at this equation right here. All right, well, it doesn't matter. Let's take a look at the second one, where it's a little nicer. So here we have the initial, 11 times S squared is what the volume is going to be. If you triple S, that becomes L times 3S squared. Now I can go ahead and rewrite this as L times 3 squared times S squared. There's nothing wrong in doing that. I'm distributing the squared to the 3 and then to the S, and then separating because they already are multiplication. 3 squared is the same as 9. So I end up with 11 times 9 times S squared, which is going to result in 11 times 9 being 99 S squared. Alright, now compared to where we started at 11S squared, the difference between 11 and 99 is that it has been multiplied by, it's 9 times greater, or 9 times larger in this case here. So what Han is saying is absolutely true. If we triple the size of the side, that is going to result in the overall volume being 9 times larger than what it was initially, right? So if we triple this size, it's going to be 9 times larger. And again, if you think about that, that means if I triple the size, this square extends from here a little further out. This one extends to here, right? And so now my base becomes a lot larger, which then if I put my 11 here, it's kind of crazy, I know. You end up with a much, much larger rectangular prism. So it's not just going to be 3 times larger, it's going to end up being 9 times larger for the volume. So what we're doing to the side by tripling it is going to make it 9 times larger. So whatever that is, if it's triple, then we square it and it becomes 9 times larger. If it happened to be double, which we'll look in a second, and we square that, that would make it 4 times larger. If we wanted to take it and if we want to make it 5 times larger, again, we would square that and it would make it overall 25 times larger. And you can go on and play with all those numbers you like. All right, let's look at the next part. We're going to skip the Are You Ready for More and look at the cones together, okay? Because it's just the basic parts of the lessons here. So there are many cones with a height of 7 units. Let R represent the radius and volume equals the volume, V for volume. Write an equation that expresses the relationship between volume and radius and use 3.14 as an approximation. So we would say that volume, we know for a cone is written, or look, volume is for a cone is going to be, the equation is the 1/3 times pi times the radius squared times the height. We're going to keep the 1/3. The pi becomes 3.14 for our approximation of pi. We don't know what the r is, so that just stays r squared. And the height, it said, was 7, so we have a 7 here. So volume, in this case, for our equation we're going to write, is the working these things out. So 7 times 3.14 divided by 3 is going to be equal to 7.33. And then we keep the radius squared. So with the relationship between V and R, it looks like this. A volume equals 7.33 R squared. So the question then becomes, what happens to the volume if you triple the value of R? And what we saw before is if we triple the value of something, that means I'm going to square that, whatever I'm doing. If I'm tripling it, I'm going to square it. I should come up with something 9 times bigger, is what should take place, if our prediction from what we did before holds true. Let's see if it works for the cone the same way it did for the cube or the prism before. So if we take our volume, and we know volume is 7.33, okay, and then we say we're going to triple 3r, the radius, so we triple the radius, 3 times that. Again, we distribute the square throughout it. We have 7.33 times 3 squared times r squared, so it's 7.33 times 9 r squared, right? So once again, because we have that 9 right there, we're going to say that's 9 times bigger, 9 times larger once again. And so you can multiply that and get your 63, whatever it's going to be, 64, and that is 9 times bigger. All right, I'm not going to multiply it out because that's what it is. If you multiply that, it's 9 times larger. So whenever you triple it, we're going to make it 9 times larger. Again, that's taking the tripling, squaring it to determine how much larger the volume is going to be. Now the next thing I want you to do is to actually graph this out. So we're going to use this 7.33, actually this one, 7.33 r squared equation. So volume equals 7.33 r squared, and we're going to graph this out. So I'm going to have a table for r and a table for the volume, like so. And at 0, it's 0, so our starting point is here. This is going to be our radius, and over here will be our volume, okay? And when r is 1, 1 squared is 1 times 7.33 is 7.33. When we do 2, this becomes 4 times 7.33, which is 29.32. 3 becomes 3 squared is 9. 9 times 7, whatever, is 65.97. When I do 4, 4 squared is 16. 16 times 7-ish is going to be 117.28. When I do 5, it becomes 5 squared, which is 25. 25 times 7-ish becomes 183.25. And I went ahead and did 6 as well. 6 squared is 36. 36 times 7-ish is 263.80. So I have several plots here, points that I can plot. I'm going to go ahead and make it every other one. So 1, 2, 3, 4, 5, and 6. I'm going up to 263, so I can actually count by 25s here. 25, 50, 75, 100, 125, 150, 175, 200, 225, 250, and 275. So at 0 we're at 0, at 1 we're about 7, so somewhere around here. 2 we're at 29, so let's say about there. 3 we're at 65, so somewhere here-ish. 4 we're at 117, so we're going to go about there. 5 we're at 183, so we're going to be about here. And 6 we're at 263, so we're up here. So this graph is not linear. We can see that it is curving up in that direction there. So we don't have that linear relationship happening, do we? All right, so that's happening because why? Because we're changing 2 dimensions, right? The radius is happening, it's just gonna be 2 dimensions there. There's 2 sides because it's the base. All right, the radius goes all the way around, it's gonna extend the whole circle out. So what happens to the volume if you triple R? If you triple R, then the volume becomes 9 times larger, is what's happening there. Where do we see that in the graph? Well, let's see, if the radius was 2, then the volume was equal to 29.32. If I triple the radius, then I'm at a radius of 6. Where's the volume at 6? The volume at 6 was going to be equal to 263.80, which if I do 29.32 times 9, I end up with something pretty close to that right there. Okay, so that's where that works there. So if I triple the radius, that dimension there, I'm going to make the volume 9 times larger. Okay, so in summary here, we kind of look at the bottom part of the summary. So why does the volume multiply by a squared when only the radius changes? This makes sense if we imagine how scaling the radius changes the base area of the cylinder. As the radius increases, the base area gets larger in 2 dimensions. The circle gets wider and also taller, while the 3rd dimension, the height stays the same. So when you think about a circle, you might think, well, that's just 1 r, right? 1 radius. Well, when this grows, if I triple that out, just say here, the circle is going to get larger in more than 1 direction. That's different than if I had a square and I just made it a little bit longer in 1 direction like that. Okay, that's a different thing. So when I'm looking at 2 dimensions, the radius works that way, just like that. So that's why that works there, because it's growing in more than 1 direction. So we're going to make sure we do the right thing. All right, let's pause there, do your homework, and then let's take a look and check it out together. All right, it says there are many cylinders with a height of 18 meters. Cylinder, 18 meters, there it is. R represents the radius and V the volume. Write an equation that represents volume as a function of R. So we know volume for cylinder is equal to pi r squared h. We have our volume is equal to, our h is 18, so we can write 18 pi r squared. So there's our equation that represents volume as a function of R, right? As a function means it's what we're setting by itself. So the volume depends upon the radius. Complete this table giving 3 possible examples. All right, so knowing we have that equation, if the radius is 1, then that becomes 18 pi. No problem. If the radius is 2, then what happens? Then volume equals 18 pi 2 squared. 2 squared is 4, and 4 times 18 is 72 pi. All right, now what happens if we do 3? 3 becomes 18 pi 3 squared, and 3 squared is 9. 18 pi times 9, and 18 times 9 is 162 and pi stays where it is. All right, so while this is increasing by a little bit, we can see the volume is increasing by a lot more. So if the radius of the cylinder is doubled, does the volume double? Looking here we doubled it, right, times 2. What's happening to there? That's not times 2, that's actually going to be times 4. Why 4? Because 2 squared. So we would say no, and you want to explain that there to say that no, it's actually multiplied by 4, and the reason for that is that we are going to square whatever we're doing. So doubling is 2, and we square it to make it 4. Is this graph of this function a line? We would say nope, it's not going to be a line. Again, if we were to graph this out 1, 2, 3, and maybe do some different lines here, we would see this is going to have an upward curve. It's not a linear function. We can tell by the points that are there. It's not going to form a straight line. Number 2. As part of the competition, Diego must spin around a circle 6 times and then run to a tree. The time he spends his spin is represented by S, and running is an R. He gets to the tree in 21 seconds after he starts spinning. Write an equation showing the relationship between S and R. All right, so he's going to spin 6 times, and then he's going to run, and it's going to take him a total of 21 seconds. So that's our equation. Spinning 6 times plus the run time equals 21 seconds. All right. Rearrange the equation to show R as a function of S. This is going to be R equal S, right? So that's like our Y is an X thing. So we want to get the R by itself. So to do that, we can keep the R here. We can keep the 21 there. And to move the 6S over there, we subtract 6S. So we have R equals 21 minus 6S. So R is a function of S. If Diego takes 1.2 seconds to spin around, how many seconds do you spend running? So let's figure that out. That's going to be using the equation R equals 21 minus 6 times 1.2. 6 times 1.2 is equal to 7.2. So 21 minus 7.2 is 13.8 seconds. That's what our value of R would be. The next page says the table and graph represent 2 functions. Use a table and graph to answer the questions. So there's 2 different functions here. They're not the same. We have a graph function and we have a table function. All right. So for which values of x is the output from the table less than the output from the graph? Okay, so here's our x. I'm going to just do the graph values here in a separate little part. I'm going to join them to the table. Not because they're connected, but just so I can compare. Right? So for our graph, when x is 1, y is about 2.2. Okay? We want to look for where this is less. Is this less than that? Nope, that's not going to work. It's too big. Next one, when x is 2 in the graph, we're at 3.8. 3.8. Is this less? Yes, that one is less than that. Answering the first question, right? I wanted to find out where this is less than that. Okay, at 3, y is at about still 3.8. Is that less? Yes, it is. At 4, we're at 2.5. Is that less? Nope. At 5, my graph is at 0. Is this less? Nope, it's bigger. And at 6, I have over here at negative 2.5. Is this bigger? No. So where in the table are the values of x less than the values of the graph? That's going to happen at 2 and 3. That's where those values are less than those values. What does that mean? I don't know. We're just comparing 2 things. In the graph function, which values of x give an output of 0? So where is the y value equal to 0? Our output is going to be our y value. So where is y equals 0? Here, here, and here. So where is that? It's when x equals 0, 5, and I'm going to say 10 because I think it probably should go through the 10. It may not be perfect. Maybe it's 9.9. I'm going to go ahead and say 10. All right. And I think our last one here, a cone. A cone has a radius of 3 and a height of 4 units. What's the volume of the cone? Volume equals 1/3 pi times radius squared times the height. So 3 squared is 9. 9 times 4 is 36. So we have 1/3 pi 9 times 4, 1/3 pi 36, and 36 divided by 3 is going to be equal to 12. So we have the pi by itself still, so we have 12 pi becomes the volume of that cone, 12 pi. Another cone has quadruple the radius, that's 4 times as much, right? 4 times as much, and the same height. How many times larger is the new cone's volume? So what we're going to do, we're going to take the radius, okay, it's 4 times as much, and we take what we're doing, 4 times it, and we square that amount. So 4 squared is equal to 16, so it should be 16 times larger would be our solution there. Whatever we're doing, 4 times, 3 times, 5 times, we square that, and that tells us how much larger the volume will be, 16 times larger. That's it for today's lesson. We'll see you next time.